we had derived the governing equations for perturbation. So we had derived this so-called Orr-Sommerfeld equation, which is basically the fourth order PDE. So if this is y direction velocity perturbation, so we had said that u is, let's say, this is base state, and then the pressure in base state was, let's call it u naught. So pressure in base state was mu d2 capital U over dy square. So using this equation, you can solve for the pressure in the base state. Okay, and then if you look at perturbed state, so that there you have u naught plus epsilon u prime, and you have p as p naught plus epsilon p prime, and then you linearize your governing equations in u prime, u vector prime, and p prime. You linearize these governing equations, and then we had obtained a system of equations to condense it in a simpler, in a rather simpler form. We had combined those four equations into a single fourth order equation, which looked something like this basically. Then we had del v prime over del x equals nu v prime. Okay, so this is your equation that we had derived in the Cartesian coordinates. This is how the equation looked like, and then for channel flow, we said that the boundary conditions can be, for channel flow, the boundary conditions are that v prime is 0 at plus minus h by 2. So, y equals plus minus h by 2 for all x and z, v prime is 0, and then we had derived using continuity equation that since del u prime by del x is 0 and del w prime by del z will be 0 on the walls. So, on walls, I am not saying they are 0 everywhere, they are 0 on the walls. Okay. Why? Because u prime is 0 on the wall due to no slip, and wall is a plane in xz plane. Okay. It is a surface in xz plane. So, it is 0 at all x locations on y equals minus h by 2 and plus h by 2. So, I can differentiate it in x or z. Okay. There is nothing wrong with differentiating it in x and z. You cannot differentiate at y. Okay. It is a value specified at y, at a given y location, you cannot differentiate it at y, but you can differentiate in x and z. So, this, from this you say that del v prime over del y on the walls is 0. Okay. So, you have four boundary conditions for your fourth order ODE that we had converted this equation to. So, we had written that this v prime is basically v hat kx kz y, and then a function of, let us say, omega as well, e to the power I kxx plus kyy minus omega t. So, using this normal mode assumption in space and time, we had derived an equation for v hat which looked something like this. So, we said it is, let us say, I alpha of u minus c, and then we had d2 minus k square, oh, I kx, there is no alpha beta in the notes. So, and then minus I kx d2u over dy square, this whole thing multiplied by v hat equals nu times d2 square minus k square whole square v hat, where this d, capital D, is d by dy and k square is kx square plus k z square. Okay, this is your fourth order ODE for the mode of velocity perturbation v prime. Okay, this is called the mode, or you can call it the amplitude. Why is it called the amplitude? Because just if you just look at this expression, you know that this part is the wave traveling part. Okay, this is the wave traveling part, where your wave is not propagating only in x or y, x or z, it is propagating in z also. Okay, it's not propagating only in x or z, it is propagating x only or z only, it is propagating in both directions. So you have a wave number in both x and z, and then this is like an amplitude variation in y. Okay, so the wave has a propagation nature in x z, and it has some function, some unknown variation in y that you evaluate from here. So v hat is, you can call v hat as the amplitude function. Okay, in some textbooks you will see this being called as modal function, or there are multiple names that may be called. So you have to understand from the context what are they talking about in different literature. Okay, so we are just going to call it as amplitude. Okay, in this course, as far as we are concerned, for us this will be an amplitude, and amplitude is not constant. That's what I want you to think about. Amplitude is not constant in space for us. Okay, now what is the interesting thing? One interesting thing that we see is, so we did this analysis for channel flow. Let us say you are doing this analysis for Kuwait flow. Okay, what do you have in Kuwait flow? What are the conditions? So you have something similar. Let's say you have plates like this, you have x, you have y, you have z, and then at y equals plus h by 2 minus h by 2, you have this as moving at a velocity, let's say u naught. Okay, in this case, what is your base state velocity? What is your base state velocity when you have this kind of a situation? Huh? What is the base state velocity when you have this situation? Wet flow, this is like a flow due to a wall that is moving. Capital U as a function of y is simply u naught times 1 minus 2y by h, or 1 plus, right, or y by h, half plus y by h. So it is basically u naught by 2 into 1 plus 2y over 2h, right, because at y at plus h by 2 this is u naught, and at y equals minus h by 2 this is 0. Okay, so the base state velocity looks something like this. It's a linear profile, right, and in this case your pressure is constant, p naught is constant. Okay, so as you can see, base state involves deriving all those steady flow solutions that we have derived in this course, or that we tend to derive in this course. Okay, any of those could be your base state. Okay, this from the simplest ones to slightly more complicated ones, any of those could be your base state. So this is something that you should remember while preparing for your exams as well, that stability is an addition on top of whatever we have been doing so far. Any steady flows for this course, any steady flow solution that I have derived, I could ask for you to evaluate its stability or some properties of its stability. Okay, so stability corresponds to analysis which is on top of whatever we have done so far, that is finding steady laminar solutions. We are trying to derive stability of those. Okay, so similarly for boundary layers also you could understand stability, and if you look at our boundary layer equations, you will see that you can study stability by making these kind of assumptions, by making this assumption particularly. We will discuss that after we discuss Couette flow. So one interesting thing for Couette flow that happens is, so what is the simplification that happens with Couette flow in your final this or Sommerfeld equation? What simplification do you see? Hmm? What simplification do you see for Couette flow happening? d2u by dy square is 0. So this term goes away, and your stability equation that you are left with is Okay. So, you can rearrange this equation and then, so let's divide this LHS by nu, okay, and let us look at this equation. So, you can write d2 minus k square of d2 minus k square minus this whole thing I k x capital U minus c over nu times V hat equals 0. Okay. Remember that even for Couette flow the boundary conditions are same. These are boundary conditions for perturbation. So, in your Couette flow, let us say you add the perturbation to your velocity. Let us say you do this, u is u naught plus epsilon u prime. Okay. Then you substitute the boundary condition that u at y equals plus h by 2 is equal to u naught, let us say I cap. In that case, this u naught I cap and and capital U naught I cap coming from this base velocity will cancel out, and eventually you will get that perturbations at the wall are still 0. Okay. The biggest mistake that most students make here is that they will see this u naught and they will say, okay, perturbation also has a boundary condition of u naught at the top wall. It is a perturbation. The wall is fixing the velocity of the fluid to be u naught. So, that means the perturbation will be 0 there. The wall is fixing through no slip. So, perturbation is still 0. So, all of these things that we derived actually they apply for Couette flow as well, because apart from x direction velocity all other things are straightforward. Okay. Walls, these are hard walls. So, V prime is 0 on both the walls and these things also apply. So, this also applies. Okay. So, this is a simplified equation that you end up with, and so here C, let me just write it down for completeness. C we had derived C we had defined as omega over kx. Okay. So, in your temporal stability analysis that we are going to mostly do in this course, in your temporal stability analysis, if imaginary, or if let us say omega, if imaginary of omega is not equal to 0, then you have instability. Okay. This is something we have shown, that if your frequency has complex, uh, if your frequency is complex, it has imaginary component which is not 0, then there are very good chances that it will have it will be complex conjugate. So, there will be a plus imaginary part and a minus imaginary part. So, in either of those cases you will end up with an instability in one of those cases. So, for temporal stability analysis we say this. So, since omega or C is defined as omega over kx, and again for temporal stability analysis kx and kz are real, so you can say the same thing about the wave speed. So, if imaginary of wave speed is not 0, then you have instability. Hmm? Hmm. No, that is what I wanted to highlight, that any derivative of base flow term is different from the derivative of your unknown. Okay. Because base flow, they are differentiations in y, but we tend to not write this as capital D because base flow is known to you. Okay. So, you should look at this. So, in some textbooks you will see this as written like this, because this is something that you won't substitute, this is something that you won't put like, okay, I will put capital U, I will have a operator in front of capital U and then I will solve for capital U also. Okay. This is a known function technically. So, that is why I have not written it as capital D2 times U. Okay. But yeah, you're right. It's just differentiation in y. I'm trying to differentiate that differentiation because one is differentiation of the unknown, which is basically giving you an ODE to solve, and the other is some known function. Okay, so you can write it whatever way you want. Okay, so my point here is that if imaginary of C not equal to 0, then we have instability. Okay, and what about real part of C? What can we say about real part of C? Hmm? What can we say about real part of C? Is there anything that we can comment on for the real part of C? Hmm? So I'd ask you to go home and think about it. What can you say about real part of C? And if you look at this equation, are there some more simplifications that you can do? Okay, verbally, what you can do is you can shift to a coordinate frame that is not a translating coordinate frame because capital U is not constant in y, but let us say you are looking at the perturbations propagating relative to the flow. Okay, and in that case what you can do is you can solve this equation. You can simplify this capital U minus C very easily, and then you can try to solve this equation. This is simply a fourth order ODE. Okay, so for example, if I gave you this, what is the solution of this? V hat equals e to the power a e to the power ky plus b e to the power minus ky, right? Those are the two solutions for just one of this operator. For the other operator also you can solve this. Okay, so in Couette flow, due to dropping of this d2u by dy square, there are some simplifications you can do, but in general shear flows where you don't have the luxury of cancelling this d2u by dy square, then you have to deal with this equation. Okay, now dealing with this equation is not straightforward. Dealing with this equation is not easy. There are no and there are very less analytical things that we can do with this equation. One thing that we can definitely do is not with this equation, but this whole analysis is assume perturbations to be inviscid. Okay. Now this is a very strong assumption, but the idea behind this assumption is that your perturbations are so smooth that the viscous terms are almost negligible. Okay, that your perturbations are so small and smooth that you can ignore any viscous contribution to those perturbations. Okay, in a way you can think about it like this, that the perturbations that you have, okay, so you know that for inviscid assumption to work there has to be some form of Reynolds number that has to be very large. Now these are perturbations, these are small, you can't have Reynolds number which is large based on large velocity or something, but there is a length scale involved with perturbations. Okay, there is a length scale involved with perturbations, and the idea that we are basing this assumption on is that the length scale of perturbations is very large. That is, let us say you have a channel of this length. Okay, then you have a perturbation which has a length scale equal to this length. The channel's height is, let's say, very much less than this length. You have a perturbation in that channel which is of the order of this length only. Okay, so in that case the length scale is very large compared to the transverse, this h guy. Okay, so you can say that my perturbations are existing over very large length scales, so they are mostly smooth, and we can assume that perturbations are inviscid, and in that case your equation simplifies a lot. This equation simplifies a lot. Okay, so you will see that this right hand side we are ignoring, and we are trying to write this Orr Sommerfeld equation into a simplified equation that becomes this guy. So I'll cancel out ikx from both the terms, and I'll be left with v hat equals d2u over dy square v hat. Okay. So I can write this equation again as now what I am going to derive is a criterion from this equation, that within the assumption of inviscid perturbations, can we derive a criterion to understand when is a flow stable or unstable. Okay. Using this equation we can do that, we can do some mathematical manipulation and derive that criterion. So what I am going to do is I am going to multiply this equation with complex conjugate of v hat and integrate from minus h by 2 to h by 2. Why I am doing this? That is something that you can just accept for now. Okay. But what I am trying to do is basically derive the criterion. How do we motivate that this is the step that you need to take to derive that criterion? That will come through practice. I mean, I could say that yeah, we are trying to calculate the equation for an energy norm of perturbations, but you won't understand anything in that. Okay. So let's try to not think about why doing this. Let's try to accept this and then see how we can derive a criterion from this. Okay. So can you repeat how we went from there to there? No, this is separate case. I went from here to here. This is just a case that I wanted to discuss where you have one simplification, okay, where you can derive the solution using this kind of a expansion of a solution. So that is d square minus, so the solution of this equation will be, you have a fourth order ODE, you will have 4 basic solutions that you linearly combine, 2 of them will be this and 2 of them you can derive by solving for this operator. So let us look at the stability from this part. Okay, let us see if we can get a criterion for stability from this part. By the way, I hope everyone understands that this v hat is not necessarily real. Okay, this v hat, if you look at this v hat, this v hat is not real. V prime is real, of course. V hat is not necessarily real. Okay, Fourier transform of a real function doesn't have to be real. Okay, so this is complex conjugate v hat star, and now let us open this up. So you have this v hat star k square v hat dy, which is basically k square times mod v hat square dy. Okay, k square times mod v hat square dy. Notice that this is always greater than equal to 0. Okay, this is integration from minus h by 2 to h by 2. This is mod v hat square, that is always a positive quantity. You are integrating it over a finite domain. So k square is also a positive quantity. So you have this as greater than equal to 0 always. Okay. Let us look at the other one. So you have v hat star d2 v hat dy. Now here we can do some business of applying by parts. So we can do v hat star dv hat from minus h by 2 to h by 2 minus dv hat star times dv hat dy. What can you say about this term? What can we say about this term? Let us say for channel flows. We are doing this for channel flow. What can you say about this term? Hmm? What can we say about this term? V hat star dv hat minus h by 2 to h by 2. Okay, channel flow, Couette flow, whichever one. What can you say about this term? What is dv hat at h by 2 or minus h by 2? 0. So this term is 0. Okay. So the left hand side is basically minus of h by 2 to h by 2 So, this term is minus of h. So, this is dv hat star times dv hat. So, this is mod dv hat square dy, and then a plus of, I have taken minus outside, plus of k square minus h by 2 to h by 2 mod v hat square dy equals v hat star by capital U minus c d2u over dy square, and then a v hat, let us multiply it here, dy minus h by 2 to h by 2. Okay. So, what can you say about the right hand side quantity? You see that left hand side is always a negative quantity. Left hand side is always negative, right? This is something positive integrated over a finite domain. This is something positive integrated over a finite domain. Okay. The left hand side is always negative. You have a minus outside in both of those terms. So, left hand side is always negative. Now, let us see how we can use this. Okay. Let us see how we can use this. One another thing is that this guy is real, always real also, you know. Okay. This is always real, there is nothing imaginary here. So, what we can say is, so what we can say is that the imaginary part of minus h by 2 to h by 2 mod b hat square over u minus c d2u over dy square dy equals 0. Imaginary part of this guy is 0. Okay. Imaginary part of this guy is 0. Now, within this integrand, which term do you expect to be imaginary? Within the integrand, what is imaginary? What can be imagined? What can have complex values? C only, right? It's the wave speed that can have complex values only. This guy. So, how can I convert this imaginary into imaginary of C? I can multiply divide by, u plus C or something else. U minus C is a complex number. So, complex conjugate of u minus C. So, what will I get? Mod v hat square by mod u minus C square into u minus C star d2u over dy square, imaginary of this whole thing integrated equals 0. What is the imaginary of this whole thing? So, imaginary of this is basically imaginary of this is imaginary of this, and u minus C star is nothing but u minus C of star. So, imaginary of minus of C of star is basically imaginary of C. So, mod v hat square by mod u minus C square times imaginary of C and then d2u over dy square equals 0. So, that means this integral should be 0, okay, for inviscid perturbations. For inviscid perturbations, this integral should be 0. Now, focus here on the left hand side, this quantity is always positive. By construction, this quantity is always positive, mod v hat square by mod u minus C square, this is always positive. You are saying that imaginary of C times d2u by dy square times something positive, integration should be 0. Now, integration of this term of this integrand can be 0 if it crosses some sign from minus h by 2 to h by 2, right. Let us say you are discussing or you want to find, notice imaginary of C should not be 0 for instability. So, for instability for instability, that is when imaginary of c is not 0, the only way this integral can be 0 is if d2u by dy square crosses 0 between minus h by 2 to h by 2. That is the only way this whole integral can be 0. Okay, that in some region this is positive, in other region it is negative, so they are summing up to be 0. There is no other way for this integral to be 0 for unstable cases. Okay, for which cases is this integral always 0? For which cases will this integral always be 0? When your imaginary of c is always 0. What do we call such cases when imaginary of c is always 0? Neutrally stable, not just stable, neutrally stable. Perturbations are neither growing nor decaying, they are just as they are. Okay, whatever you give the perturbations and energy externally, they will maintain that energy for infinite time. Okay, so d2u by dy square crosses 0 between this. What is that point called when second derivative crosses 0? So basically, if you look at capital U versus y, okay, the idea is that your second derivative should cross 0. That means the first derivative should have either a maximum or a minimum, right. So let us say, I am going to move this. So you have these two cases that are possible when your velocity could have instability. So one case is something like, let us say this, and the other case is something like how do I make it like this. If you had either of these two variations, then you will see here what happens to du by dy. It starts with something positive, it is increasing and then it is decreasing. So somewhere here du by dy is maximum. Okay. Now here du by dy, it starts with something very positive, it is decreasing and then it is increasing. So somewhere here du by dy is minimum. So both of these velocity profiles could be unstable. We are not saying they will necessarily be unstable, but they will definitely be unstable. What we are saying is that inviscid perturbation should hold this criterion, and within this criterion these velocity profiles could be unstable. Okay, but if they don't have an inflection point in between, then definitely it cannot be unstable, because if you don't have an inflection point, then this equation itself is not held. Okay, so this is a necessary condition, not a sufficient condition. Okay, that d2u by dy square crosses 0 between minus h by 2 to h by 2, this is a necessary condition but not a sufficient condition, and this is called Rayleigh's criterion. So we see this guy's name appearing everywhere in fluid mechanics, right. I always mess up his name spelling, because why not. Which one is it, IE or EI? It's EI, I think. Yeah, this is called Rayleigh's criterion, and this is not a this is not a sufficient condition, but it's a necessary condition for your inviscid perturbations to be unstable. Okay, and this step of multiplying with v hat star and then converting it into a integral criterion, this step you can apply this step to almost all of your instability analysis. Okay, as we will see, I mean we won't derive this particular equation for that case, but we will see when you have, so there is another instability case which is very easily reproducible also in lab, that is when you have a Taylor Couette flow. So just like that, that's a Couette flow. A Taylor Couette flow is basically that in cylindrical coordinates. You have two cylinders, one of them is fixed, the other one is rotating. Okay, and if the omega difference or the angular velocity difference between these two cylinders crosses a critical value, then you start to see streaks appearing in between the cylinders of in between the flow. Okay, and those streaks are basically instability that is developing. Okay, and for that case also you can do something very similar of an analysis and derive a criterion when or which what is that critical value of omega difference that after which you will see instability. How did we ignore the u term? U is always real, no? Imaginary part of that term is 0. No, just take the imaginary part of this term. What will you get? This is real. This will be only imaginary of C. This is real.
What is this Rayleigh's criterion is necessary condition of?
It is necessary condition for instability. Instability of inviscid perturbations. Exactly.
So you said sufficient but not necessary.
Necessary but not sufficient. Why is it not sufficient? Because if you think about it, we just said, okay, we just commented that imaginary of C should not be 0. We did not say if imaginary of C should be positive or negative or what. Okay, one is that. The other is we had this equation and we only said that okay, imaginary of this is 0. We never said that real part of this should be equal to this also. Okay, that's just half of the maths that this guy did in a way. Okay, so let's criticize him a bit. Why not? Okay, he saw this equation and then he said, oh, imaginary of this should be 0. Yeah, but real part of this should be equal to this also. This is a complex equation, so you have to do equality for both real and imaginary parts. Okay, and that's what a Swedish guy came after him who did that. That okay, let's improve this criterion a bit, equate the real parts also, and he derived a so-called improved criterion, which is called the. Again, his name is also very confusing. It's called Fischer-Tropsch's criterion. And you know this guy is going to do math when he has a P in his name. Okay, although that's in their language, so I shouldn't say that. But so then you have this real part of. So he derived the condition by saying that real part of this should be mod d2u by dy square dy should be equal to this term. What is this term? This is always negative. So this should be always less than equal to 0. Okay. Now real part, to convert this into a real part, we can say that okay, this is minus h by 2 to h by 2 mod v hat square by mod u minus c square, and then a real part of u minus c star, which is going to be simply u minus real of c t2u by dy square dy. This integral should be less than equal to 0. Let's hold on for a bit. We'll answer that question in 2 minutes. When can that criterion be hold? Okay, to look at that, so I can do a trick of saying, hold on. So what I can do here is I can define a, let's say I can define a u bar. Okay, let us say I can define a u bar and minus h by 2 to h by 2 So I can write this u minus real part of c. So let's write this all together, and this u minus real part of c. So we can write it as u minus a u bar. We'll just comment what this u bar is, and then a plus of. So I'm going to basically hold on. So u minus real part of c dy. Now I'm going to add same thing, minus h by 2 to h by 2, and then a real part of c minus some u bar on both the sides. Okay, so this should be less than equal to this term, minus h by 2 to h by 2 mod v hat square by mod u minus real part of c minus u bar dy. Let's get rid of everything else. So I've just added on both sides a term, and let us comment what this u bar is. Okay, this u bar is such that, so this u bar that I am defining, this u bar is nothing but 1 by h, let us say, minus h by 2 to h by 2 u dy. Okay, this is some mean velocity. This is some mean velocity between the channels. Okay, this is some mean velocity between the channels. Now our job is to show that, so now our job becomes that on the left hand side what you see happens is minus h by 2 to h by 2 mod v hat square by mod u minus c square d2u by dy square u minus u bar dy should be less than equal to this term. Okay, should be less than equal to this term. Now a criterion that this guy derived is by say, so as far as the argumentation goes is that what is the what is the what is the value that this term can take based on our previous discussion. Okay, what is the value that this term can take based on our previous discussion. So let us say you have an inflection point in between. So d2u by dy square is crossing 0 somewhere, and this term is always positive. This is crossing from plus to minus. Okay, now let us say what is this term actually. So let u bar be equal to c. Okay, not the mean velocity. U bar is some c value. So the idea is that, let us say you have this flow and you have your u velocity that is varying between these two, however it might be varying. Okay, I am just giving some random variation that satisfies Rayleigh's criterion. So let us say your capital U is varying something like this. Now what I am trying to say is capital U is has a variation between this, between these walls, and let us say you have a value of c such that, let us say you have a value of c such that capital U is equal to that c at that y location. Okay, for example, this is your capital U, this is versus y. Let us say real part of c is something like this. Okay, in a lot of instability analysis, this particular y location, okay, so this particular y location where this holds, so c has a number, c is not varying in y, c is a number. Okay, c is a number of the flow, characteristic to the flow or characteristic to the perturbations, and if you have a y location where your capital U is equal to c, then notice what I discussed in our previous section, that you can transfer yourself, you can transform the frame to some value of capital U, and you can look at the perturbations in that frame. In a frame that is that is traveling with this u bar, the perturbations will be stationary. In a frame that is traveling with the u bar velocity, the perturbations will be stationary. Okay, and this particular y location where you have u equals u bar is called the critical location. Okay. Now, this has very important implications. What happens near this critical location? Okay. Actually, as you will see in some advanced instability textbooks, there are problems that start appearing here. Okay, things start to become singular near this critical layer, and you have to entertain the possibility of viscosity in your perturbations. No matter how smooth your perturbations are, you have to entertain the possibility of viscosity. But let us try to stay clear of that criterion and just say, okay, u bar is this real part of C. So that means this quantity should be less than equal to 0. Okay, so I picked a u bar which is equal to real part of C, and I am saying, okay, this is less than equal to 0. So I just basically wrote that this is u minus u bar.
So the earlier formula that you had written for u bar, that is not valid.
Yeah, that was not correct. Please fix that. U bar is this, not a mean velocity. I mean, it could be correct, but that's not how u bar is derived. You could have a situation where u bar is this. Okay, you could have a situation, but that's not how u bar is defined. And now this criterion is called Fischer-Tropsch criterion, and you can think about when this will hold. Okay, when this criterion will hold based on your inflection point criterion or the Rayleigh's criterion. Okay. So, as you can quickly think about it, that this quantity is always positive. So, that means this d2 u by dy square times u minus u bar should cross 0 between minus h by 2 to h by 2. Okay. U bar is basically real part of C. This should cross 0 from minus h by 2 to h by 2. Only then this integral can be equal to 0 or less than 0. Okay. Now coming to the question, okay, is this sufficient? Is this sufficient? And the answer is no, because sufficiency for instability means that you have to have that imaginary part of C to be not 0, and you have to have one positive part, one negative part. Actually, if you think about it, you had e to the power I k x x minus omega t. Okay. So, you can take kx common, and you can write this as e to the power I kx x minus ct. The only way this is going to grow in time is when the imaginary part of C is what? Imaginary part of C is what when this grows in time? This is minus ICT. Imaginary part of C should be what? Positive. I times I will be minus 1, minus 1, minus 1, plus 1. So, if your imaginary part of C is not just not equal to 0, but also positive, only then you have instability, and that is a sufficient criterion. All other criteria that you derive for your from your these equations, you are just equating things. Okay, you are just equating things based on your governing equation. You are not deriving something new. Okay, all of this information, both Rayleigh's criterion and Fischer-Tropsch criterion, they are hidden in your governing equation itself. Okay, there's nothing new, there's no new information that you are deriving from these equations, from these criterion. They are all hidden in your governing equation. So neither of them can be sufficient. They will be necessary because the perturbations have to satisfy the governing equations necessarily, but for sufficiency you need to have a positive imaginary part in your C. Only then you can say for sure, yeah, this is instability.
Why should it be positive? Because T will grow.
Yeah, because there will be exponential growth in time.
Another thing, why should it cross 0? In this case, it has to be negative. So
Less than equal to 0, of course, it has to be negative. So, this part is always positive. Okay. And u minus u bar, you can think about u minus u bar, a quantity that will never be always negative. Okay, u minus u bar will never be always negative because u bar is somewhere a value of u. So, below that or above that, either of them, it will be less than u bar, greater than u bar. So, this quantity will also cross a 0 somewhere. this quantity must cross a 0 somewhere based on Rayleigh's criterion for instability. So, the product should cross a 0 somewhere based on this criterion. Okay, and you can obtain that location of y if you know what is that critical location, but that is somewhat
to apply is equal to 0 in this.
Huh?
If it was purely negative, then we wouldn't need to cross 0.
Even then you would have to cross 0, right?
Cross 0. We already had this condition implied.
So separately they cross 0. What I'm saying is for this to hold, the product should cross 0
That so because d2 by dy square is anyways crossing 0.
for instability. Yeah.
How we have defined u bar, u minus u bar is also. So this is not really.
This is certainly what you're trying to say is by construction of it, this might always be true. The criterion might always be satisfied, and you will be right. Okay, that u minus u bar crosses 0, d2u by dy square crosses 0. So why just formulate a criterion which is always satisfied? Well, blame that guy, not me.
This criterion is for stability.
For instability, everything is for instability. Now you can see that this criterion, technically, this criterion is for neither stability nor instability. This criterion is just a criterion for this equation to be satisfied. Okay, both these criterion were evaluated from the governing equation only. As I said, there's nothing new that I added in this analysis. I'm just doing mathematical manipulation of the same governing equation. I can't obtain new information from it. Okay, so think about these criteria as criteria for this equation to be satisfied by the V perturbation. Okay, now we have obtained some. So this criterion, for example, is necessary for this equation to be satisfied. The Rayleigh's equation that we have derived, it's necessary for the condition to be satisfied, for this equation to be satisfied. Now after that we said, hey, the instability requires this to be non-zero, so that means for an unstable case this should happen. Okay, we said that for instability after that. Now here we did not comment anything about the imaginary part of C. Okay, so technically this equation is not really a criteria for instability. This equation is a criteria for this equation to be satisfied. Okay, we did not take anything about imaginary of C. Okay, and now some of you might be thinking, okay, you have done all of this algebra. Where does this connect back to our starting discussion on instability? And for those of you, I would say, if you look at your equation for unstable for inviscid perturbations, then in here this C is the eigenvalue. How I can say this C is the eigenvalue? Basically, I can write this equation as C times d2 minus k square we had equals u minus u double prime we had u times d2 minus k square. Okay, and just like a generalized algebraic eigenvalue problem is something like this. So you have a v equals lambda bv. This is your generalized eigenvalue problem in algebraic sense. In differential sense, you can have some function. So let's write this C here, where these L1 and L2 are linear differential operators. Basically, what we have here, d2 minus k square, d2 minus k square, and things like that. This is called a differential eigenvalue problem. This is called an algebraic eigenvalue problem. Okay, for those of you who have taken the numerical courses, you know that these differential operators, when you discretize your space, you know that these differential operators can be written as a matrix. Okay, so whenever you are doing any discretization, you are essentially approximating these differential operators, which are infinite dimensional operators. You are approximating them as finite dimensional matrices, linear operators. Okay, so that is the abstract layer on what these differential operators essentially mean. When you try to go ahead and compute them numerically, they become linear operators in the vector space sense. or algebraic sense. Okay. So, I am just trying to give a congruence between why I call this as an eigenvalue problem, because when you try to solve it numerically, this will convert to this, because these operators will convert to matrices, because when you discretize, that is what happens. Okay. So, if you relate this back to our discussion of, okay, calculate the eigenvalues of Jacobian and then estimate what instability is, yes, the C here is the eigenvalue of this problem. Okay. So, we have not lost that particular connection so far, that there are eigenvalues that are being calculated. Someone is finding that very funny, I do not know why, but there are eigenvalues that are being calculated, and we are looking at imaginary part of those eigenvalues.